Welcome to UKSing Maths. In this lecture, I am going to explain polar form of a complex number, equality of two complex numbers, and various algebraic properties of the complex number. Now let us see what is the polar form of a complex number. This polar form of a complex number is known by various names. It is also known as trigonometric form of a complex number. It is also known as the modulus argument form of a complex number. Let z equal to a plus ib be a complex number. Then we know that this complex number can be represented in the complex plane by an ordered pair AB. Let the point P represent this ordered pair AB in the complex plane as shown in the diagram. By using very basic concept of geometry, you can easily visualize that this A, which is the real part of the complex number z, denotes the x coordinate or abscissa of this point P, that is distance OM is equal to A, and the imaginary part of this complex number, that is B, represents the y coordinate of this point P or the ordinate of this point P, that is PM equal to B. Then using the Pythagoras theorem, in the right angle triangle OPM, you will find the value of r equal to a square root of a square plus b square. And also by taking the trigonometric ratio of cos theta and sin theta, you can have the relations of the form a equal to r cos theta and b equal to r sin theta. And also by dividing b by a, you will have a relation theta equal to tan inverse b by a. And do remember these relations what I have highlighted over here. This r is nothing but the modulus of this complex number z, and this theta is nothing but the argument of this complex number z. We have already studied these formulas in the earlier lecture. We have our complex number z equal to a plus ib, and we have just derived two relations, a equal to r cos theta and b equal to r sin theta. Now let us put the values of a and b in this z equal to a plus ib. You will find the final relation z equal to r in the bracket cos theta plus I sin theta. And this relation, this equation z equal to r under bracket cos theta plus I sin theta is known as polar form of the complex number. And you can easily visualize by seeing this relation that there are two main ingredients necessary to represent a complex number in polar form. They are modulus, that is r equal to a square root of a square plus b square, and amplitude of this complex number, that is theta, which is tan inverse b by a. We know the value of the exponential function e power I theta equal to cos theta plus I sin theta. So in light of this exponential function, the equation 1 can be rewritten as z equal to r e to the power I theta, and this form of complex number is known as the Euler form of the complex number. Now let us see the relation between the rectangular and polar form of a complex number. This rectangular form is also known as Cartesian form. We all know about the Cartesian coordinate system. This coordinate system is named in the honor of 17th century mathematician René Descartes, because he invented such type of system in which two perpendicular fixed lines intersect at a point known as origin, and with the help of a pair of coordinates known as x coordinate and y coordinates, or abscissa and ordinate, any point can be uniquely represented in the plane. We have just derived these four relations which you are watching on your screen. A equal to r cos theta, b equal to r sin theta, r equal to square root of a square plus b square, and theta equal to tan inverse b by a. This will be very helpful in conversion from one system to another system. Now let us see how to convert a complex number from rectangular form to polar form. We have just seen that in polar form, a complex number is represented with the help of two main ingredients, r and theta, and we have already seen the relation r equal to a square root of a square plus b square, and theta equal to tan inverse b by a. So with the help of the relation r comma theta equal to square root of a square plus b square comma tan inverse b by a, you can easily convert a complex number in rectangular form to polar form. Only you have to use r equal to square root of a square plus b square and theta equal to tan inverse b by a, and a and b are already given in the rectangular coordinate system. So with the help of that, you find the values of r and theta, and then write this complex number z in the form z equal to r under bracket cos theta plus I sin theta, and you will have the result. Now let us see the conversion of a complex number from polar coordinate to rectangular coordinate. In polar coordinate, r and theta is already given. You simply find the value of r cos theta and r sin theta, and we know this conversion formula a equal to r cos theta and b equal to r sin theta, and with the help of this r and theta, a and b can be evaluated. Now let us understand this fact geometrically. For every point a comma b in the complex plane except origin z equal to 0, we can have a unique polar coordinate r comma theta, where r greater than 0 is the modulus of the complex number and theta is the principal argument of the complex number, so must satisfy one of these inequality. For z equal to 0, the argument of a complex number is not defined, so a complex number is exclusively represented by its modulus, that is r equal to 0. This polar form is very useful and used in proving various algebraic relations in a very easy manner. Polar form establishes a relationship between trigonometric functions and algebraic functions. We already know about the exponential functions, and various trigonometric ratios can be expressed in terms of that exponential functions or Euler form. Now let us understand this concept of polar form with the help of an example. Suppose z equal to 1 plus I be a given complex number, and you are asked to find the polar form of this complex number, and in addition to this you are also asked to find z to the power 6 and the modulus and argument of this complex number is z to the power 6. Now let us understand these one by one in an algorithmic view. Firstly, to convert in polar form, we have already seen the relation. You have to put a equal to r cos theta, b equal to r sin theta, where r is the modulus of this complex number and theta is the argument of the complex number. So here a is 1, so put 1 equal to r cos theta, b is also 1, so put 1 equal to r sin theta, and with the help of these two equations find out the value of r, which comes out to be a square root of 2, and the value of argument theta equal to tan inverse b by a, which comes out to be 45 degrees. So here the modulus of this complex number, that is r, is equal to square root of 2, and argument of this complex number theta is equal to 45 degrees. Now our task is to convert this complex number z equal to 1 plus I into the polar form, and we have already evaluated the value of r and theta. Now simply use the relation z equal to r under bracket cos theta plus I sin theta, and you already know the value of r and theta. So the polar form of the given complex number z equal to 1 plus I is z equal to square root of 2 under bracket cos 45 degree plus I sin 45 degree. Now let us see next part. We have to find z to the power 6. In case of exponents and all, it is very convenient to convert this complex number into the Euler form, that is z equal to r e to the power I theta. You simply raise by power 6 both sides. You will have z6 equal to r6 e to the power I6 theta, and say this is equal to capital R into e to the power I phi. So in this way you can visualize here that this capital R is the modulus of this complex number z power 6, and this phi is the argument of this complex number z power 6, and you can easily see that this capital R is equal to a small r to the power 6, and this phi is equal to 6 into theta, and you already know the value of r and theta. So you simply put these values of r and theta in these relations, you will find the modulus of this complex number z power 6 is equal to r power 6, which comes out to be 8, and argument of this complex number z power 6 comes out to be 6 theta, which is 270 degree. Now let us concentrate on one more concept of complex number, that is equality of two complex numbers. Two complex numbers are said to be equal if their real and imaginary parts are separately equal. What I mean to say, let z1 equal to a plus ib and z2 equal to c plus id be the two complex number. Then according to this definition of equality of these two complex number, z1 will be equal to z2 if and only if a equal to c and b equal to d. That is, real part of first complex number must be equal to real part of second complex number. The imaginary part of first complex number must be equal to the imaginary part of the second complex number. And there is a wide application of this concept, and many problems are solved using this concept of equality of complex number. Now let us understand this concept with the help of very simple example. Suppose you have z1 equal to 2 plus yi and z2 equal to minus x plus 3i, and it is given that these two complex numbers are equal. Then find the value of x and y. Very easy. Using the concept of equality of complex number, you already know that two complex numbers are equal if and only if the real and imaginary parts are separately equal. And using this concept, you will find that value of x comes out to be minus 2 and value of y comes out to be 3 here. A complex number is said to be equal to 0 if both of its real and imaginary part are equal to 0. Suppose z equal to a plus ib be our complex number. Then this z will be equal to 0 if and only if a equal to 0 and b equal to 0. Now let us understand one more concept. In case of real numbers, we know that if x and y are two real numbers and x square plus y square equal to 0, then both of these real number x and y must have to be 0. But the case is different with the complex numbers. If z1 and z2 are the two complex numbers, then z1 square plus z2 square equal to 0. It doesn't necessarily implies that z1 and z2 both are 0. It may be non-zero. Now let us verify this concept with the help of two simple examples. Take z1 equal to 1 minus I and z2 equal to 1 plus I. When you find z1 square plus z2 square, you will get 0. But here neither z1 nor z2 is 0. Now let us understand this very important concept of complex numbers, that is, complex number do not possess the property of order or inequality. Whatever we have studied in real numbers, any real number can be expressed as greater than something or less than something. But in case of complex number, that does not hold good. Now let us understand why complex number do not possess the property of order. We already know that a complex number is visualized as a point in a plane. It can be represented by an ordered pair in the plane. And since a point do not follow the property of order in a plane, that's why a complex number do not follow the property of order. So suppose a plus ib and c plus id be the two complex numbers, then a plus ib less than c plus id or a plus ib greater than c plus id are not defined in the complex numbers. You can see by this simple example that you cannot write 1 plus 2i is less than 6 plus 9i or 3 plus 4i is greater than 2 plus 3i. These are absurd things, have no sense. But one thing you have to note that the modulus of a complex number definitely possesses the property of order, because we already discussed that the modulus of a complex number is treated as some sort of distance, and a distance possesses the property of order. That's why modulus of a complex number possesses the property of order. So if z1 and z2 be the two complex number, then we can write mod z1 less than mod z2 or mod z1 greater than mod z2. This type of relations are very much defined and have sense in case of the modulus of the complex numbers and all. Now let us concentrate on algebraic properties of complex numbers. First, see the addition of two complex numbers. Suppose z1 equal to a1 plus ib1 and z2 equal to a2 plus ib2 be the two complex numbers. Then its sum is given by z1 plus z2 equal to a1 plus a2 plus I times b1 plus b2. Easily visualize over here that in case of sum of complex numbers, the resultant complex number has real part, which is the sum of the real parts of these individual complex numbers. Similarly, the imaginary part is the sum of imaginary parts of these individual complex numbers. You can understand this simple concept with the help of a small example given on your screen. Now let us see subtraction of complex number. Let z1 equal to a1 plus ib1 and z2 equal to a2 plus ib2 be the two complex numbers. Concept wise, this operation of subtraction is not very different from the operation of addition, because subtraction of z2 from z1 is treated as addition of minus z2 in z1. So the formula for subtraction of two complex number is very similar to that of the addition of two complex number and can be expressed as z1 minus z2 equal to a1 minus a2 plus I times b1 minus b2. You can easily visualize that in case of subtraction, the resultant complex number has real part, which is the difference of the real part of the individual complex numbers, and has imaginary part, which is the difference of the imaginary part of the individual complex number z1 and z2. Now let us understand the multiplication of complex numbers. Suppose z1 equal to a1 plus ib1 and z2 equal to a2 plus ib2 be the two complex numbers. Then their multiplication is denoted by z1 into z2 and is given by z1 into z2 equal to a1 a2 minus b1 b2 plus I times a1 b2 plus a2 b1. You can easily visualize that in case of resultant complex number z1 into z2, the real part is nothing but the difference of the products of the real part and imaginary parts of these individual complex numbers. The imaginary part of this resultant complex number z1 into z2 is the sum of the real part of first complex number into imaginary part of second complex number and imaginary part of first complex number into real part of second complex number. Now let us understand the division of complex numbers. Suppose z1 equal to a1 plus ib1 and z2 equal to a2 plus ib2 be the two complex numbers. But naturally, this second complex number z2 is not equal to 0, means mod z2 is not equal to 0. The division of z1 and z2 is denoted by z1 by z2. z1 by z2 is given by a1 a2 plus b1 b2 divided by a2 square plus b2 square plus iota times a2 b1 minus a1 b2 divided by a2 square plus b2 square. Here complex number z2 is not equal to 0, that is mod z2 is not equal to 0. Now let us understand these simple properties one by one. The closure law with respect to addition and multiplication holds for complex number. What I mean to say? Now let us understand this basic concept of closure property. Suppose X be a non-empty set and an operation star is defined on it. Now let us suppose A and B are two arbitrary elements of the set X. If A operation B also belongs to the set X, then we say that the set X is closed with respect to operation of a star, or closure law holds good on this set X. In case of complex number, we have already seen that if z1 and z2 are two complex number, then z1 plus z2 is also a complex number. So the set of complex numbers is closed with respect to operation of addition, or closure law holds good on the set of complex number with respect to addition. Similarly, we have seen that if z1 and z2 are two complex number, then z1 into z2 is also a complex number. So the set of complex number is closed with respect to operation of multiplication, or closure law with respect to multiplication holds for complex number. Now let us see next property. Commutative law holds with respect to addition and multiplication of complex number. The concept of commutative law is like that: if X be a non-empty set and an operation star is defined on it, and let A and B are any two arbitrary element of this set X, if A star B equal to B star A, then we say that commutative law holds for this set X. Now let us see in case of complex numbers. If Z1 and Z2 are two complex numbers, then Z1 plus Z2 equal to Z2 plus Z1. So the commutative law holds with respect to addition for complex numbers. In the similar way, Z1 into Z2 is equal to Z2 into Z1. So commutative law holds with respect to multiplication for the set of complex numbers. Similarly, associative law holds with respect to addition and multiplication of complex numbers. Suppose Z1, Z2 and Z3 are three complex numbers, and firstly add Z2 and Z3 and then add this resultant Z2 plus Z3 to Z1. It will be same as you firstly add Z1 and Z2 and then add this resultant Z1 plus Z2 to Z3. This is known as associative law. For multiplication, you can see the relation on the screen. Similarly, distributive law holds with respect to addition multiplication for complex numbers. There are two types of distributive law, left and right distributive law. You can visualize on this screen and all. Now additive and multiplicative identity both exist for complex numbers. Let a plus ib be a complex number, and suppose c plus id and e plus if be the additive identity and multiplicative identity respectively. We already know the basic concept of additive identity. If you add additive identity with a number, the resultant is the same number. So if c plus id be the additive identities, so if you add with the complex number a plus ib, the result will be simply a plus ib, and through this relation you can find the value of c and d, which comes out to be 0. So 0 plus I0 is the additive identity, and it is denoted by 0 in case of complex numbers. Similarly, the concept of multiplicative identity is also same. If you multiply the multiplicative identity with any number, the result is the same number. So here e plus if be the multiplicative identity for the complex number a plus ib. So a plus ib into e plus if must be equal to a plus ib, and with this relation you can find the value of e and f, which comes out to be equal to 1 and f equal to 0. So 1 plus I into 0 is the multiplicative identity for the complex number, and it is denoted by 1. Now let us see the next concept, the additive and multiplicative inverse for a complex number. Let z equal to a plus ib be a complex number, and let c plus id and e plus if be the additive inverse and multiplicative inverse respectively for the complex number a plus ib. And you already know the basic concept of inverse. If you operate the inverse with the given number, the resultant is the identity element and all. So if c plus id be the additive inverse of a plus ib, then a plus ib plus c plus id must be equal to additive identity, which is 0 plus I into g. And from this relation, the value of c comes out to be minus c and d comes out to be minus b. So minus a minus ib is the additive inverse for the complex number a plus ib, and it is denoted by minus z. Now according to the basic concept of multiplicative inverse, when you operate this multiplicative inverse with the number, the resultant is the multiplicative identity. Here e plus if is the multiplicative inverse for the complex number a plus ib. So when you multiply a plus ib into e plus if, the resultant is the multiplicative identity, that is 1 plus I into 0. And by solving this equation, you will have e equal to a by a square plus b square and f equal to minus b by a square plus b square, provided a square plus b square not equal to g. If you simply put these values of e and f, then the value of the multiplicative inverse comes out to be a by a square plus b square minus I times b by a square plus b square, provided a square plus b square not equal to 0. And you can also rewrite this formula of multiplicative inverse in terms of conjugate of complex number z and the modulus of the complex number z as conjugate of z by modulus of z whole square. Naturally, mod z not equal to 0. Now multiplicative inverse of a complex number is same as the reciprocal of a complex number. Now let us visualize this concept. Let z1 and z2 be the two complex number, and z1 into z2 equal to 1. Then they are called the multiplicative inverse of each other. But by this relation, you find out that Z2 is nothing but 1 by Z1. So 1 by Z1 is the inverse of Z1. Thus you have clearly visualized that the multiplicative inverse is same as the reciprocal of the complex number. Suppose you have to find the multiplicative inverse of the complex number 1 minus I into square root of 3. Then it is simply equal to 1 by 1 minus I into square root of 3. And by rationalization and all, you can find out the multiplicative inverse. Similarly, if you are asked to find the multiplicative inverse of 3 plus 4i by 4 minus 5i, you can use the same concept of reciprocal of a complex number as the multiplicative inverse, which comes out to be the value which is shown on the screen. Now thank you for watching UKC Maths. If you wish, you can like and subscribe UKC Maths, the YouTube channel, to stay connected with us. You are free to comment on the content of the article and suggest any improvement, if any. Your suggestions are always welcome and highly appreciated. Thank you.